3 is a satellite problem, and it's also one where we're looking for the radius. So when we sum up our centripetal forces, we have to set them equal to mr squared. Mr omega squared. So if this is the sun, so if what I have here is the sun, and we have a planet orbiting it, then I'll just make, oops. So I'll have a planet that's orbiting the sun, and the only force that's keeping that satellite in orbit is the gravitational force of attraction between the planet and the sun. So that's going to be Fg. So if we sum up our forces in the centripetal direction, we're going to get Fg. And like I said, it can either be mv squared over r or mr omega squared. But because in this particular problem we are looking for the radius of the planet's orbit, then we don't have a choice. We have to use mr omega squared. Like I said, the reason why you have to use that is because if we use mv squared over r, we don't have all of our r's exposed, and we're trying to isolate r. Even though there would be an r in the equation, we wouldn't have them all in the open so that we could isolate them. So there's my equation. So the next thing I'm going to do is I'm going to replace Fg with the formula for Fg, which is G m1 m2. So m1 m2, I guess I can use subscripts for one of them is going to be the mass of the planet, and one of them is going to be the mass of the sun, divided by r squared. And you can put whatever you want. You can just put m1 and m2 if that's fine. You can just put a subscript for the sun, as long as you show that the mass here is different than the mass here. So that's going to equal mr omega squared, and the m on the right side is going to be the mass of the planet, because that's what's orbiting. So there is your equation. So the next thing is we can cancel out the mass of the planet on both sides. And if I solve for r, what I'd be doing, I'm going to try to do this in one step. I'm going to be moving, if I multiply both sides by r squared, then I'd only have the numerator here, the g and the ms. And if I multiply this side by r squared, I'm going to get r cubed. So we need to get rid of the omega squared. If I divide both sides by omega squared, it would come down here. So what I'll have is r cubed there and gms over omega squared there, solving for r. So in one step, since r cubed would equal g times the mass of the sun divided by omega squared, that would equal r cubed. So I need to take the cube root to get the r. So you can see it's sort of a neat problem in that, what I mean by neat is that I don't have stuff all over the place that I'm solving for. I just, I can solve it in, a couple steps. I've got a very simple picture. I've got a very simple equation. And then it's just algebra after that. So I know I have g because that's a constant. So I know I have that. The mass of the sun, I think, is on the formula fact sheet, right? And then the omega, I'm going to get the omega based on that they're telling me that the sun rotates once every 26 days. So that means that I want the planet to go around the sun once every 26 days. So my starting point for my omega, my starting point is going to be 1 rev every 26 days. And I need that to be in radians per second. Anytime you have omega, it has to be radians per second. So I'm going to do that in a few steps here. I'm going to go from rev to radian. I'm going to go from day to hour, and I'm going to go from hours to seconds. And that'll be the conversion, and then I'll have all the numbers that I need to substitute in. So 1 revolution is we move through 2 pi radians. In 1 day, 24 hours, and in 1 hour, 3,600 seconds. So if you work that out, what do you get? 2.80 times 10 to the negative 6 radians per second. So now I've got all the numbers I need to calculate the R. So let's go up a little bit here. I'll do it over here. So I'm going to have R equals the cube root of G. G is the universal gravitation constant, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So that's on your formula fact sheet. The mass of the sun is what? It's like 2.0 times 10 to the 31st. Is that 30? 2.0? 2.0 times 10 to the 30th kilograms. And we're going to divide that by omega squared. Now you can almost figure out what the, based on, let's say just looking at the Earth. We know how far the Earth is from the sun, 93 million miles. I could convert that into meters. If we knew the mass of the Earth, based on other things, there's other ways we can get the mass of the Earth, we can figure out the mass of the sun. So this number, we can figure this out based on, if I know we're 93 million miles away, I know what the universal gravitation constant is, I know it takes us 1 year to do 1 revolution. So with these numbers, I could actually rearrange it to solve for the mass of the sun if that was something that I didn't know. So down here, I'm going to have 2.80 times 10 to the negative 6 radians per second. So I'm forced to use radian, but again, as far as a unit, we can ignore it. We know the answer should end up in meters. So if we actually cancel all this stuff out, we would get underneath here, we would get underneath the cube root, we would get meters cubed, but when I take the cube root of it, we would get meters. So if you solve this, what was the answer? Was it 2.57 times 10 to the 10th? So 2.57 times 10 to the 10th meters. Now, we're done here, but what I'm going to do